Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back. Students, welcome you all in flexure analysis and design of beam. And in this lecture, inshallah, I will covering almost 20 examples of flexure analysis and design of beam. Okay, so almost 20 examples. In which we will basically cover analysis and design of simply supported beam, analysis and design of cantilever beam, and analysis and design of overhang beam. Okay, I am covering these examples from MC Cormic book 10th edition, and these are the exercise examples which I will going to cover. Okay, so before starting this discussion or these examples, first of all I would like to present you some important informations which is regarding to design aids. And these design aids, basically if you are working as a professional engineer, these design aids will help you a lot. Okay, first of all I would like to present this important graph. Okay, remember, most of the students basically confusing in this diagram or in this graph, and don't understand what this diagram basically mean. Before, if you are going to analyze any flexure member, any compression member, you have to basically understand this diagram. Okay, this is basically the diagram which is a relationship between pi value and strain value of steel. Okay, you all know pi value and epsilon t. Remember, this diagram basically represents 3 stages. Okay, the one stage which you see here, this one, okay, which is basically a linear stage, and then it becomes inclined, and then again it becomes linear. Okay, so these two are the boundary condition, you can say. This is this limit is basically, you can see the phi value here, you see here 0.65, where here you see the epsilon t, that is the strain value, 0.002. It must be remember. What does it mean? This means that when your epsilon t value is 0.002 or lesser from 0.002, you have to take the phi value equals to 0.65, and this means that your member is in compression. Okay, the member, let's say you are designing a beam, let's say you are designing a slab, that will be a compression control section. Remember, this thing is very important to understand. Whenever we are designing a flexure member, we have to design them as under reinforced section, or you can say tension control section. Okay, you already know over reinforced section, under reinforced section, and balance section. So we always try that our section is under reinforced, or you can say tension control. So the other limit is this one. Okay, here your pi value is 0.9, and this is the case which we already used in our calculation. Pi value almost we use 0.90, but most of the students do not know that what is basically the purpose of this 0.90, where it comes from, where we have to change, or whether it is a fixed value or constant value. But this is not a constant value, it may change when your epsilon t value is less than 0.005. Remember, if your epsilon t value is 0.005, your phi value will be 0.90, or if your epsilon t value is more than 0.005, your phi value will be 0.90. This is remember. And if your epsilon t value lies in between this region, this is epsilon t is more than 0.002 but less than 0.005, then you have to interpolate epsilon t value from this equation or either from this equation. If you are a spiral member, then you will use this one. If you are other member, not spiral member, so then you have to use this equation. Remember, this equation or this graph is basically for grade 60 reinforcement. So these formulas will be applicable for grade 60 steel. Now, there is very important information. If you are not interested to calculate your epsilon t value is what you can calculate epsilon t value. I will show you the formula for epsilon t. Okay, but on the other hand, if you are not interested to calculate your epsilon t, then you can calculate your c divided by dt value. C divided by dt value is 0.600, then your pi value will be 0.65. If your c divided by dt value is this much, then your phi value will be 0.90. If it lies in between these regions, then you have to choose your pi value by this interpolation formula. This is remember. Now, you see here, basically when this condition exists, your C divided by TT value is less than 0.60 but greater than this one, mean that your value is somewhere here. Okay, so that's why we are using this interpolation formula, but this is in the case for 60 KSI steel. Now for example, if you are a steel which yield stress is not equals to 60 KSI, let's say 40 KSI, 50 KSI, 70 KSI, then you have to replace this value by epsilon y, and epsilon y is what? Fy divided by Es. E is 29,000, Fy is, let's say this is 40 KSI or 50 KSI, so you got that one. Okay, remember this 0.002 is basically nothing, it is 60 divided by 29,000, it will give you 0.002. Similarly, if you have a 40 KSI steel, then you have to just plug the value 40 divided by 29,000. So here you got. Okay, so this graph is very important when this condition exists. Epsilon t is greater than epsilon y but less than 0.005. This is, remember, this condition exists. So we basically use these condition in our calculation. Okay, so that's why I'm just giving you a little bit knowledge about these things. This diagram is very important. Look out to this diagram. You see the graph which is coming in this diagram, and here it stops. A little bit increase up to C point and then it become a linear. What does it mean? This means there you see the rho value. The rho value basically starts from 0.02. Remember, your rho value increases. Your rho value increases, your capacity of your member is increasing. But here you see your rho value is increasing but your capacity is not increasing. Why? What the reason? The reason is the pi value. Okay, when you increasing your rho value up to a certain limit, what does it mean? You got your pi value 0.90. Okay, but when your rho value reaches to rho max, remember, rho max. So once you reach to rho max, remember, once you reach to rho max, then this value again going down. Okay, it adopts a lesser value than 0.90. Remember, that is related with epsilon t. This is very important. Okay, this means that if you are using more steel reinforcement, remember, your epsilon t will not reaches to 0.005. Remember this value, you are not reaching to 0.005. This means your epsilon t value will be increases, will be decreases. They will going toward this side, and once you are going to this side, your pi value decreases. So on the other hand, if you are increasing your steel ratio and you are thinking that your moving capacity will be increased, so this is here you are wrong. Okay, you have to use the maximum value of pi, and that maximum value can be used, that is 0.9, when your epsilon t value is 0.005. Remember, 0.005. This is important. If you cross this limit, then remember epsilon pi value will be 0.8786 and there will be decreases. So if this value decreases, your moment capacity will be decreased. Okay, so this graph is very important to understand. Remember, the next thing, the rho minimum value, you already know this value. We have to calculate our rho minimum value from these two equations. Rho balance, already you must know rho balance. Remember, this is the rho balance equation. 87,000 divided by 87,000 plus Fy. Now here you have to plug the actual value of your Fy. Let's say you are using 60 KSI, then here you have to plug 60,000. Remember, 87,000, basically this value is in PSI. If you divide this by 1000, so then you 87 divided by 87 plus 60 KSI. If you are plugging values in KSI, then just ignore these values and you have to plug values in 60. Remember, this is in KSI. If you are interested to convert them into strain values, sometimes you see this value 0.003 divided by 0.003 plus 0.002 will be in this case, because this is Fy. Now you just need to divide this 87,000 divided by 29,000. You got this value 0.003. Okay, so that will be the strain value. You can use either stress, you can use either a strain value. But remember, rho max is the value. Remember, if you replace this Fy here, you just plug the value of strain, but strain equals to epsilon t. Remember, this is very, very important. This information is very, very important for you people. Now let me show here. Okay, I will show you. Remember, rho max is the same formula, the same values, but here if you are using your maximum strain of your concrete divided by maximum strain of your concrete, okay, plus 0.0005, this is important. So then that rho B, that is the rho balance, will become rho max, and here you are basically imposing that condition that your strain, this is epsilon t value, epsilon t must be equals to epsilon y, mean that if your epsilon y value must be equal to epsilon t or greater than epsilon t, then this value is okay. Otherwise, if you are using the actual value of epsilon y, then it is not will be equals to rho max, and you have to check your ductility. Okay, so I will explain all these things, but I will just want to explain you the difference between rho b and rho max. Remember, the other thing, that is epsilon t. From here, inshallah, we will discuss this equation and we will calculate the ductility check from this epsilon t. If you are using whatever the steel, you have to just need to calculate your effective dip, and C value is nothing, it is just equals to A divided by beta 1. Okay, so you know A is F divided by 0.85 if C prime into B. Now these are the values which we can use for determination of the depth of this beam as well as for the depth of the slab. Okay, and I already discussed it. If you have a 60 KSI steel, then you have to multiply these coefficient with this factor. Remember, and this thing is very important. It is a new knowledge for you people, I think so. For example, what should be the minimum width of your beam? Remember, there are certain ACI criteria that your width of the beam should minimum width. How much minimum width is you needed for number of bars? For each number of bars, you have specific minimum width of the beam, and they will be determined. Remember, from the center of this bar to the far edge or to this edge, the distance can be calculated in this way. Remember, the minimum clear cover equals to 1.5 inch. The gap, remember, there is a gap when you bending your stirrup. Remember, this is not 90 degree. Okay, here you have we keep some kind of space. That space is basically equals to 2 times of ds, or you can say the diameter of the stirrup. So that gap and then the distance up to the face. So that distance is basically 2.5 by 8, okay, inches minimum. And this is the way how you can calculate the minimum width of the beam. Remember, this formula will be used. The minimum width of the beam will be calculated from this formula: cover plus dia of the stirrup plus that gap plus diameter of the bar divided by 2 plus then again diameter of the bar, then again diameter. For example, if you have 2 bars here, then this will be the case when we have 2 bars here, 1 bar and other bar, and then 3 bar. Okay, we have 3 bar here. This is not for this beam. Okay, we have 3 dia bars, then again the next dia bar plus 2ds plus ds, again that thing will be repeated here. And for number 10 bar, basically if you are using for number 10 bar, and you have how much bars? 1 2 3 4 5 bars. Okay, you have 5 bars, number 10 bars. The minimum width which your beam is needed 10.4 inch. Now if you are using more than 5 bars, number 10, let's say you are using 6 bar, then you have to provide the bars in 2 layers. These are the ACI criteria. Remember, then you have to use how to calculate your moment capacity. This is I already discussed this equation in one of my lectures. Basically, if you don't watch this lecture, okay, basically I use this in this equation, that in this example, basically I use that equation. Okay, and this is again the other provision of ACI, which is a skin reinforcement. When your H is increasing more than 3 feet, then you have to provide skin reinforcement. And what is skin reinforcement? Inshallah, that are basically provided to control the strains. Also, it can control torsion as well. Okay, so I will discuss it inshallah in sometime in next other lectures. But you have to provide the skin reinforcement if your beam is a deep beam. Okay, not a shallow beam. This is an ACI design aid table. I basically choose it from Nelson book. Okay, and this R is nothing. Okay, it will be like this much. I discussed basically in this example. So please watch this lecture series. I already uploaded this analysis by ACI movement coefficient, and I explained this equation. Okay, so I don't want to waste my time on this graph, but I will use this. Okay, now next these are the design aids, and inshallah you will see how we will use these in examples. Okay, now let's start basically example number 4.5, and these are the example. These are the data basically. This is the example problem sections, and these are the example. Let's start. You see we have a beam, and beam loads are given, and let me change. Okay, now loads and values are given. Beam weights are not included. Remember, the beam loads are not included. Already you know the loads are given, which are the imposed loading, live load, dead load, but the beam weight are not included. And the capacity, the density is given, and the depth will be d plus 2.5 is the effective cover. Okay, and d you have to calculate d. Now this is the beam, and the basic purpose of these examples are to know about the variation when your yielding stress is changing, your FC prime changing, your length changes, what will affect, how it will affect on d, how it will affect the reinforcement. Okay, so basically here the reinforcement ratio which is given rho for the two examples. For the two first examples you have to use this one, and for the one you have to use 50% of the rho b, and here you have a given strain ratio is given. Okay, now let's start. This is example number 4.5. Assume weight of the beam. Remember, weight of the beam is assumed because the weight of the beam is not included in that dead load. Remember, so we have to assume basically in the initial stage, and then if our assumed weight is greater than the calculated weight, so design is okay. If the calculated weight is more than assumed weight, then we have to repeat the calculation. The weight of the beam is assumed round about 15 to 20 pounds per feet. For example, we have, you see here in the first case 30 feet span. So if you assume 20 pound per feet, so 20 times 30 give you 600. So you can assume 500 pound per feet weight. Then again you have to calculate WU, which is nothing 1.2. 2 is the dead load, and 0.5 is basically the weight of the beam, and 1 kip is the live load which is given here. Okay, 1 kip is given, 2, and the weight of the beam, that is 500 pounds. So converting to kips you got 2.5 pound. So weight is calculated, movement is calculated. Now this is the steel ratio, and it is already given here. Rho is 0.1 at FC prime divided by Fy. So we got rho is equal to 0.012. Okay, now once we got this rho, we have to now calculate what we need further. Remember here we have MU, that is 517.5 feet. Now against this rho value we have to calculate this value. So from table A13, this is a design aid. So from design aid we got this value. So how we can get this? Let me show you the design aid A13. Table A13, basically I have that table as well. Table A13 is this one. Okay, now here you see I have 60,000 and 40,000, 4,000 concrete and 60,000 steel. So here I have to search 0.012. Okay, 0.012. So 0.012 round about this one. Okay, so this is the rho value and this is the MU value. Here I have 643.5. So that is the reason I got this one. Okay, now from this I have to find out BD square. So that why they will be shipped, this value will be shipped here and BD square will be here. Now once I did the calculation, here you see all the whole calculation, and I got 10,723. Okay, now remember these are the options available for my beam sizes. If I keep my width of the beam 14 inches, then my effective depth will be this much. If I keep 16, then my effective depth will be this much. And if I keep my width equals to 18, then my this much. So here I have different options. let's say I'm using 16-inch width, okay, and 29-inch the total depth. So I'm using this option, okay. So 25.89 plus 2.5, you got round about 29 inches. So my effective depth is repeated because 29 minus 2.5 it gave me 26.50 inches. Now I again recalculate the beam of weight. So beam of weight means 16 times 29 divided by 144 times 150. I got 483, which is less than 500. So this is okay. If it is greater than this one, so I have to repeat my calculation. Clear? Now again I have to find out my area of steel, that is nothing rho times BD. Okay, so rho is already calculated, BD is already fixed out, and my steel area is this much. Now let's say I'm using 4 number 10 bars, so it give me 4.06 inch square. Again I recalculate my rho value because remember I needed this much and I'm providing this much. So my rho will be changed now. This is 0.0119, okay, and it is greater than rho minimum. Rho minimum is what? Because if you are using a 4000 psi steel, and remember I already from this diagram it is basically clear that your rho minimum for temperature and shrinkage reinforcement, for example this is grade 60 and grade 40, okay. So your rho minimum value will be 0.00. basically from that equations you can calculate, okay. The equations which I already shared you, 200 divided by Fy or 3 ipsi prime and root divided by Fy. From that equation you got this one 0.00. We already know that for grade 60 and 4000 concrete you have this much is the lower value of your rho minimum. Rho max is basically from table A7. Now from table A7, basically table A7, let me show you here. This is very important, okay. This is very important. How can you read rho minimum value, rho maximum value, okay. This is table A7. Here you see basically here we have in this case, okay. Now 60 psi, okay, and see your this value is rho balance, okay. Here basically we have this case, okay, 4000 psi. So this value, this is my balance steel ratio, okay, and my rho, this is my maximum, okay. Remember the value which is against epsilon t, I already explained in the initial stage that if you replace what, for example I already explained this point here, okay. Remember that if you in rho b equation you replace by 0. Where that is that formula, this one, if you replace that 0.002 which is actual value by 0.005, then your rho b becomes rho max, remember. And that's why basically this is value is now my rho max value, remember. This is the epsilon t. When your epsilon t value is 0.005, the rho b which is calculated will be your rho max, remember. And now this is my rho max value. So this must be, remember, my rho max value is 0.01. So that's why basically they choose this value. So my calculated rho is greater than rho minimum but less than this one. So ductility check is okay. My pi value will be 0.90. This means that my epsilon t value, if you calculate, they must be greater than 0.005. If you satisfy your equation that your rho provided is greater than rho minimum, okay, and it is less than rho max, okay, rho max, this is important, then your ductility check will be okay. From that tables, in view of these tables, remember, in view of these tables, your ductility check will be okay and you will be allowed to use your pi value 0.90. And this is the section. Again I have to check this rho, this width, minimum width, this rho minimum, and I already add this in my table as well. Here I have add this. This is, look, minimum width in inches for beams with inside exposure. Remember this is ACI. And remember, if you are using number 10 bars, let's say number of bars in single layer. So here I'm using what? I'm using number 10, 4 number 10 bar. So 4 number 10 bar this one and number 10 bar this one. So 12.9 inch width needed for me and I'm using 16, so this is okay. because my width of the beam is more than minimum width of the beam. So this spacing will be okay. If it is less than 12.5, then I again repeat the calculation, or either I have to provide these bars in 2 layers. Okay, so this is ACI criteria you must satisfy. Example number 4.6 is same. Okay, example number 4.5, 4.6 is same. Remember here what things change. You see here again 34,000, 60,000, and all data I think so same. Okay, 0.18. Yes, again the things are same, the same equation, same loading is assumed, mu is same, rho is same, 0.012, rho max is that value, rho minimum is that value. Okay, and my again the same things. Okay, and here they are using I think so 16 times 33 section. They are a little bit larger value they are using. Okay, so that why steel is changing. 5 number 10 bars is basically they are using. And B minimum, okay, this is which is calculated from table F5 is 15.5. Again it is less than 16, so we are okay here. Okay, now the next example 4.7. So in 4.7 what I have in 4.7 50,000. Here yield stress is changed, concrete strength is changed, length is changed, loading is changed, and as well as your steel ratio is also changed. So see, let's see what basically it affect things, how it affect things. Okay, assume weight is 575 pound per feet, 500, 600 you can assume. WU again they calculated the same loading because they include that load in dead load, and okay, MU is calculated, that is 4,000, and rho B is now, rho is basically 50 times of rho B. Okay, and from where this rho B is comes out from this table. Okay, here we have this from this table. Okay, so 50,000 psi steel, and here rho B is 0. Again we have 3,000, so this one will be your rho B. So 50% of this value. Okay, so here you see 50% or 0.5 times of this value, and rho minimum value is from the same table. Rho minimum value, rho minimum is 0.004. Clear? That is your rho minimum value, 0.004. And rho max is basically, rho max here, let's see, rho max value is 0 against this value 0.00. This one will be rho max value. Okay, so rho max is this one. Clear? I think so this is clear. Now again you have to choose your R value. Basically this is R value against this value. So let me show here where this R value, that is 4,000, 40,000. Okay, we have to add 50,000 table, and I not included basically 50,000 table. Okay, so for that purpose we have to go to basically the Nielsen book or the cormic book, and we need to go to the design aids. Basically here I have, and go down, and here we have basically 50,000. Okay, so here we have 50,000. Okay, and the value is 0. Here 0.0. Okay, 0.013 I think so. This here we have. Okay, let me check it. 0.0137 roundabout 137. Yeah, in this case this one. Okay, 40,000 no, 40,000 no, not this one, this one 0.0137, this one roundabout. We are close to this value 592. What they are basically using, yeah, the same value. Okay, so this is the way how you got this value. Now again you need to find out BD. Assume your B, let's say it is 12, 14, 16. Now you did the calculation taking square root, and you got D value, that is okay, these values. Now you have option. What option you are using? We are using this option. Now again 24.49 plus 22.5, you got around that value to 28, and then again subtracting 2.5 from this 28, you got 25, and again recalculate your weight, that is this 467, which is less than 475, so we are okay. Again recalculate your AS, which is this one, find out the number of bars, we are using this one, and so finally we got for number 11 bars. Okay, remember, if you are increasing your basically your depth, as here we see we are using 28, but remember here the length is 18 feet, so the length decreased, so that's why the depth is also decreased, and the number of bars is also decreased. But remember for number 11 bar, so you have to check this minimum width. So to check the minimum width, you have to find the table. Okay, so if you have this table is available, let's say for number 11 bar, so this is number 11 and this is 4, so minimum width is needed, that is 13.8, all about almost 14 inches depth is basically available, okay, needed, and we are providing 16 inches. You can confirm this from the equation as well. How much? Okay, you can say 1.5 ds plus 2 ds, okay, plus d diameter of the bar divided by 2 plus 2 times the diameter of the bar, and plus again this term, okay. So it will also give you the minimum width. So please go to McCormick book, and the first in the initial stage I share this equation, okay. So you can, if you don't have this graph, you can use it manually as well from this equation, okay. So the next equation is this one, this is 4.8. Basically here what we have are conditions. Okay, let me show you the conditions. 4.8, this one 60,000, 4,000, 32 feet. So the length is increased, just the length is increased, load is a little bit increased, and the ratio of steel is this one, okay. So let us see how it affect, okay. So this one, so 2.6, here I am using for 640 pound per feet, okay, 640, because the length is increased. Almost, if let's say if I am using 20 pound per feet, so minimum 32 times 20, it will give me 600, around about 640 pound feet I have to edit with the dead load. So dead load is calculated, MU is calculated, and rho is already given. So rho B you needed to find out. So you can calculate this rho B from the formula which I already show you here. Okay, if you don't have a table, so you can calculate your rho B from this equation as well. It is 7,000. For here you have to use 60,000. Okay, so just plug the value, or either you can use this table. Where is the table? This one. Okay, 60,000, and my rho B is basically 0. And my steel stress is basically is how much BD square. Where is the stress value? This one, no, this one. Let me check the steel stress value. 60,000, 4,000. So already I have to use, already again we use this in one example as well, but let me check it again. 0.028 from this table. 4,000, this one, and my rho B is basically this one, 0.0285. okay, yes, 0.0285, and the rho max value will be this one, 0.0, this one will be rho max, this one will be rho B, and this value, this one, this is the minimum value. Okay, so clear? These values you need to pick. Okay, you can calculate rho minimum from those two equations which I already shared with you. You can calculate your rho B, and you can calculate this value as well, but just you need to plug the value here, where it is here 0.003 plus 0.005, so it will give you again rho max, not rho B, remember. And the rest of the calculation is same. Okay, you just need to find out your BD. Now you need to find out your 643. Again, I have already calculated this, how to select it. Okay, because now this is your rho value. Go to that table, this table, okay, 4,000 and 6,000, 60,000 table, okay, from not this one, this is for 40,000, and here we have, okay. So here you have to search that value 0.014, 0.014 basically here, 0.0142, I think so. This is the value 0.3, so 0. This one, and you see 749.4. so here you see 7, not this one, this is row, okay, this is 643 against 0.0143. let me check it, 60,000 and 4,000, yes, and the row value is 0.0143, yes, 749 it will be. Let me check it, 643.5, yeah, this one, okay, it is okay. Now it is I think so this is wrong, clear, this one is the value 749, okay. So they did the calculation taking square root. If I am using 18, 20, 22, okay, so what will be my D? So you just need to bring this D here and taking square root, you got these values, okay. Now again, this is now up to you what value you are using, okay. I am using 2029 beam cross section, so my factor depth will be this much. Again I am recalculate my depth weight of the beam, that is 6.0. again I am okay here, and again I have to recalculate my AS. In my AS 7.58, I decide the number of bars. Let's say I'm providing this much value, so see I am using a little bit larger value than the AS, so again I need to find out my row value. Now my row value is 0.0143. Now I have to check my beam minimum, whether I can provide this 6 number of 10 bars in one layer, okay. So for that purpose my beam minimum from table is 18 inches, which is less than 20 inches, so this is okay. Where is the table? This is the table, okay. Let me share with you that table. So here you see I have 6 number of bars, 6 this much, so number 10 bars, the minimum width is I needed 18 inches, so I'm okay here. Again section check, so my row is greater than row minimum but less than row max, so that why ductility check is okay, and I have to use 0.9, clear, and this is the cross section, clear. Again the next question is this one, assume beam weight, okay, the span length is now 25 feet, the dead load is 2.3, and row, now this is from table, remember here row value is not given, here epsilon t value is given. In this equation number 4.9, basically this one value is given, 0.005 you have to use. So now I have to search the row B value against 0.05. So you just need to go to the table. Here is my table, this one. And again, let me check it, which steel they are using, okay. So here 60,000, 3,000, remember 60,000, 3,000. And epsilon t value is 0.0075, this value, okay, 0.0075. so let me check here, 60,000 and yes, 60,000 and 3,000, okay. So there, here you see epsilon t value 0.0075, so I have to use now this row. This is my row value, clear, this is my row value, okay. So again, yes, this one value is selected, they find out this value against this is basically R value, okay. I discuss it in this example, okay, when I covering this example I discuss it, okay. So basically this is actually R value. Now what you need to find out this value from table, and you know how to find out from table A12, because I have 60,000 and 3,000 concrete, okay. So once you got this value, you find out this BD. So assume your B value and got your D value. Select the section, which one will be appropriate. Recalculate your depth, weight, that is 488, we are okay here. Again, area of steel, and decide the number of bars. Again, recalculate your area of steel, which will give you 4.71, which is a little bit larger value from that one. So that way you have to recalculate your row value, and again check that row value with row max and row minimum. Your minimum width from table A5 is 15.3, and again we are safe here. So this is the final. Okay, so and remember here we already on ductile side, because the epsilon t value which we are using is 0.0075. So that value is almost greater than 0.005. Okay, so here basically in this graph you can easily say that we are on this side. So if you are on this side, you can use phi value 0.9, and your section will be tension control section. Here you see your section will be tension, means under reinforced section you are using. Okay, but if you are on this side, that epsilon t value is less than 0.00, you will be on transition side, and you have to recalculate your phi value. Okay, so this ends up. The next question is this problem. We have Fy this much, unless given weight of the beam, weight of the material is given, beam weights. Here you see design rectangular section for the beam loads and row value shown. Beam weights are not included in the loads shown. Show sketches of the cross section. Okay, so this is my live load and this is my dead load. We have to include the dead load in this. Okay, 24 feet span and the row value is given. Okay, so the calculation I think so easy. Okay, only you have to PU value will be 1.6 times. This is your live load. Okay, 1.6 times of that, and here I am using 475 pound per feet as a dead weight of the beam. Okay, I am assuming. Okay, then I add this weight into the 3 kif, so I got 3.47, and here you have to calculate your moment. So W, because this is subjected to UDL as well as a point load, so in this case your moment equation will be different. WL square by 8 plus WPL divided by 4, because if you have a point load on your simply supported beam, then for the maximum moment, okay, the maximum moment will be PL divided by 4. So you have to add this with WL square by 8. So my maximum value is this one, that is the moment value. Again I need to find out your row value, which is already given. I am using this row value. Again I have to find out this value against this value. Okay, 0.012. Go to those table. The table is mentioned here. Go to table A13 and find out this value against row value. Again this value, but make sure you will be in right table. 60,000, 4,000. Okay, concrete, and find out your BD square value and suppose your B value and find out your depths. Okay, so the section which they're using is 1433 inches, and the beam weight here 481, which is greater than 475. So almost we are close. Okay, almost 475 and 481 are close, so that's why I'm not repeating the things. Clear? But okay, you need to find out your area of steel, decide the number of bars, and now again you need to find out your row value, that is your row value. Go to table S7, find out your row minimum and row max value and check it, your ductile. So here we are on ductile side. The section is tension control, and the section is tension control. Okay, and you can use pi is equal to 0.9. Clear? And also you have to check the minimum depth. So the things are simple now. You have to just for minimum width you have to use this table. So as I am using here, let me show you using here. You see that the number of 4 number 10 bars. So 4 number 10, I think so 12.12, this much width I needed, and I already uses the width that is 14 inches. So I am on the safe side. Okay. Now again the next question is repeat problem 410. Dead load is this much and live load is this much. Okay, so the only loads are changed and nothing will be changed. So the question is same. Repeat the question and did it by self. Okay, so this question is simple. Okay, the next question is this one. So live load is here on 2 points and the UDL is 1.5 K per feet. The row value is given. Okay, assume the weight of the beam, include that in the dead load, and again factor the loads, okay, and now find the moments. Now this is the equation. This is the equation. Here you have to draw the moment diagram, and I think so the moment diagram will be looks like in this shape. Okay, it will be looks like in this shape. Here in this region I think so at the mid you have a maximum moment. So W square by 8 and P. So you need to properly draw the moment diagram and then find out the your maximum moment. Here you see this is the dead load times 8 plus 32. Basically they separate the dead load, you deal from this one, and then they draw separate diagram for these two moments. Okay. So 32 times 10, basically 10 is this much. This means that the maximum movement will be at this point. Clear? And find out your maximum movement. Okay, again recalculate your row value. Now go to the table A13 and find out this value against this value. Okay, I think so it is easy, it is not difficult. This is table A13 and this is table A8. What we have basically FC prime, and my FC prime value is 4 and 60,000. So 4 and 60,000 table. Okay, the last table, the last value, this one. Okay, and here you have to search that value 0.1012, 0.012, this one, and this is 643. So this is simple. Okay, this is simple procedure. Once you find out your row value, this one, you just need to find out your BD. Okay, assume B and calculate your D value. So, finally select one section. Let me, I'm choosing this one section. So just add 29.55 plus 2.5. You got around about 33 inches. Recalculate your D, 33 minus 2.5. You got this one. Beam weight again 481, which is less than 500. So okay, again recalculate your area of steel, decide number of bars, so a little bit larger value. So you recalculate your row value again, that is 0.0120. Go to table S7 and find out your row minimum and row max, or either you can use the formulas and calculate your row max and row minimum value. Now 0.012 is more than this one but less than this one, so we are on the safe side. And our section is tension control, means under reinforced section, and we are eligible to use 0.90. Okay, and this is the final section. But the final check you have to make that for 4 number 10 bars already we need it, and we calculated we need 12.2 inch minimum weight. So already we are using 14 inches, so we are okay. Now again the next question, the same question, just only loads are changed. Clear? And the rest of the question is same. Clear? And let me show you this question. So this question is simple. You just need to find out reactions. Okay, after finding the reactions, you need to draw the shear force diagram, and once you got the shear force diagram, find out the area of this shear force diagram area, which will be your maximum moment, and maximum moment 681. This is the only trick in this question. And the rest of the thing is same. Okay, the span length is 30 feet. So you see, assume beam weight is assumed, and they will be added to this dead load, and they will be factored. Remember, you have to factor the loads. 1.6 times of this, and 2.97 plus the weight of the beam multiplied by 1.2. Remember, and row value is given, and this value is calculated against this value. So you need to go to the table A13 and find out this factor against this value. And again, BD square, find out the value of, assume the B value or find out the D value. And they are using this section. So beam weight is recalculated in 481, which is greater than 475, but already we are close, so we don't need to repeat things. Okay, there is not a greater difference. Calculate as, decide the number of bars, and recalculate your row value. Now check the limitations, and if limitations is fulfilled, so you see limitations are fulfilled, the section is ductile, means tension control section, and we are eligible to use 0.90. And this is the final section, and you have to check this width. Okay, might change. Yes, B minimum should be checked. If it is not fulfilled, for example, then you have to use these bars in 2 layers. Okay, and if you are using 2 layers, then your D will be repeated. Remember, this is not so simple. Okay, problem again, the same problem, you just again same condition, but I think so live load is changed, FC prime is changed. Okay, and weight 750 they are using. Why? Because the same length. Okay, 64, their loading is more, 4.5 kf per feet, so loading are more. So just draw the shear force diagram and then find out that area that will give you 876. So again, rho value, mu value from now, as you calculate this value, so go to table A7 and find out that this factor, this is R. Okay, so 0.0107. let me show you table A7. Okay, I have 3000, this one. Okay, 0.01. okay, here it will be, yes, 0.0107, 107, 108 and 107. So this one 560. Okay, so 560. Assume any value, appropriate value of B, and find out your depth value. Decide one section, find out area of steel, and again decide number of bars. Okay, and find out your rho. Check it with the limitations, whether it is less than rho max and greater than rho minimum, so you are eligible to use 0.9. If it not, then you have to recalculate your phi value. From what? From that formula as I explain here. Where it is that formula? This one. This is a general formula. This is for a spiral, but this one. Okay, here you have to calculate phi value. And I already uploaded one lecture that is design of W reinforced beam, which is basically on this equation, based on this equation. So I did the calculation for this. Okay, so please go to my channel and search the W reinforced beam section. Here we have a cantilever beam. So the cantilever beam is simple. In first example 4.16, this is subjected to UDL. Live load is this much and dead load is this much. And in second question 4.17, here is a point load, that is live load. So let's see, there you see 14 feet. Okay, this is very large span. This is also very large span. Rho value is given, clear, and all the rest of the things are same. Okay, the rest of the things are same. So this is 4.16, this example 4.16, clear. Assume beam weight is assumed, dead load is calculated. Okay, in the same way mu is calculated. You already know in the case of cantilever beam that how we can calculate the maximum moment. The maximum moment will be here. So WU basically, which you got WU times 14 divided by 2. Okay, this is the formula for cantilever beam, and you see 14 divided by 2 gives you 7. So this is maximum moment. Calculate rho value, find out your this factored against this one, go to table at 30. Clear? Once you got this factor, find out your BD. Okay, assume your B and find out your D. Okay, decide one section and again recalculate for weight. So weight are okay, and recalculate your AS, decide number of bars, recalculate your rho value, and your rho value is 0.012. So check it with the limitations of ACI limitations. These rho max value and rho minimum value from table S7 I already explained. And if it is okay, so your section is ductile, tension control, and remember this is cantilever section, so you have to place the number of bars in the upper portion. And again from table A5 I think so, check the minimum weight for this section as well. Okay, this is the next question. Okay, the same question, just you have a point load. So if you have a point load, so the moment equation will be a little bit different, remember. And the same procedure. Okay, there is nothing too difficult, that which will confuse you people. Okay, and problem 4.18. Yes, this is 4.14. Okay, so problem 4.18, where it is, where this example is, let me show you. This is 4 points, this example, this is 4.18. so here we have a point load. This example is same to this one, but this is changed. Here we have 30. So the moment equation will be, here will be mu max. So WU times 16 divided by 2 plus 30 times this distance. That will give you the maximum moment. So this is the only difference, and the rest of the things are same. Okay, the rest of the things are same. Let's see. The weight of the beam is included. PU is calculated. That is 30 times 1.6. MU is calculated. See, WU times 16 divided by 2, and that factor load times 16. Rho value is given, it is calculated. Now you have to search out your R, or this factor value, against this one. So go to table F13 and find out this value against this. Okay. Now you have to find out your BD. So assume B. Okay, and find out your D. Now decide one section, recalculate your beam weight, and compare this. So 731 and 750, so already we are okay. Recalculate your area of steel, decide number of bars. Now see, 8 number 10 bars, 10.12 inch square. Now rho value will be 0.0163. so go to table S7, find out your rho max and rho minimum and check the limitations. Clear? But here you see that for 8 number 10 bar, how much width we needed. Let me check it. Here we have this one. So if I'm using number 8 number 10 bar, this much, so the width which I needed 23.1, and what width I'm using 18 inch. So this is the case that I'm using 2-layer steel. Okay, so this is, you must understand, this is the reason why I'm using 2 layers. Clear? The rest of the question is same. This is for, you can say, a home assignment for you people. Okay, because live load is given, live load, only the moment equation will be different. Okay, so the moment equation will be different, the rest of the things are same, and again they are placing the same bars in one layer. So here they show you. Okay, and this is 420. So this is the same question, this one, but this is 4.20. okay, repeat problem 418. Sorry, this is problem 418. This one is problem 414, but they change the live load and length. And this is the question number 420, which is this one. Okay, so this is a home assignment for you people, and did the exercise on it. Okay, but remember one thing in the last, I want to share with you that you see the effect of the length. If you are a site engineer, you have to remember these things. If length is changed, how much number of bars I needed. So you just keep these things in mind. Remember one thing important, these tables are important, and these tables are basically on basis on these equations. Remember, on these equations and rho max and rho minimum equation. So you must remember. And these examples are just only for flexure, not for shear, not for torsion, not for any shrinkage reinforcement. Remember, this is just only to give the idea about the flexure reinforcement, how we can calculate flexure reinforcement. So see you in next lecture, inshallah. I will covering the rest of the question, okay, which is left it here, and inshallah in that lecture I will cover the rest of the examples. Okay, so go to my cormic book and do a little bit practice on it. Okay, and see you in next lecture, because around about 20 examples are remaining. I will did those examples in that lecture. So see you in next lecture. Thank you.